Okay, good morning calculus class. So here's the other part of the video for sections 4.3. First derivative, second derivative, increasing, decreasing, concavity, line tests. So part 2. Okay, so let's see. Okay, so now here's the continuations. So for the other example 4, so use the given graph to find the following. So the first part of it, you want to find out the increasing interval. So for the increasing interval that we have, so since we do know that the graph is almost like considered increasing, but okay, so this one shows that the scale, it's 1 unit to the right, 1 unit up. So started from here down the bottom, so at 2.5, all the way to the top right here, which is 12. So that means the entire interval is considered increasing. So this one is not the xy coordinate, so this one is just the interval notation. So let's put the notes on this one. Okay, so this one is considered an interval. Okay, so for the interval, from 2.5 to 12, so it's increasing. And then part B, so the open interval on which f is decreasing. So decreasing is that from 0 to 2.5, and also 12 to 14. So you try to extend the x-axis, you'll see that 14. And then for part C, so the open interval on which f is concave upward. So if that's concave upward, so this one from 0 to 5, so that's part of it, concave upward. So this one's supposed to be a open interval from 0 to 5. And then also 7 to 10. So 7 to 10, count it, 7, 8, 9, 10. It's also considered concave upward. And then for part D, the open interval, on which f is concave downward. Again, open interval, not the closed interval, so this one there's no bracket involved. So from 5 to 7, 5 to 7, and then from 10 to 14, so it's all considered concave downward. Okay, so this one right here. Oh, the reason why that I put a bracket, because this one is the end point. That's why we need to put in the closed bracket. So that's right the first time. And then for part E, the coordinate of the points of inflection. So the points of inflection, we do have 5, 0, because this one shows concave upward, downward. So the point of inflection, so start with the first one, 5, 0. And then 7, 4. Again, concave down, concave up, so another point of inflection. And then from 10, 8, so that's the xy coordinate. So the rest of this, from A to D, those are the interval. But for the last part of this one, so this one is all about the xy coordinate form. Okay? So again, anytime the graph is given, the original function, you can always find out about the concavity. And now the next one. So for example 5, the graph of the derivative f prime of a continuous function f is shown. So this one is not the original function, it's just the first derivative. And then on what interval is f increasing or decreasing? Okay, so if that's increasing or decreasing, so we need to find out the sign change. So again, this one is just the first derivative, so we need to find out the sign change. So we do know that everything above the x-axis, so f prime of x is positive, and then anything down below the x-axis, so f prime of x is negative. As you can see that what I put in for the boundary here, so from 0 to 3 it's positive, and then from 3 to 5 it's negative, and then from 5 to the point right here looks like it's less than 8, so this part here is also positive. So on what interval is f increasing or decreasing? So for that increasing interval, so it's from 0 to 3. And also increasing from 5 to 8. Okay, so that's the increasing interval. Now, what about for the decreasing interval? For the decreasing interval, it's only from 3 to 5. 3 to 5. Okay. And then for part B, at what value of x does f have a local maximum or minimum? Okay, so we do know that this part is considered positive, negative. So if that's positive, negative, so that means for the original function, it's considered increasing and then decreasing. So that means at 3 right here, so we do have a local max. So at x equals 3, we do have a local max. And then for the minimum, so that means it's from negative to positive, decreasing, and then increasing. So at x equals 5, we do have a minimum. And on what interval is f concave upward or downward? Okay, so concave upward or downward, so that means it's about finding the second derivative. So again, this one is just the first derivative. So as you can see that the part of the graph right here, it's all decreasing from 0 to 4 right here. So that means from 0 to 4, the graph is considered concave down. While the whole graph for f prime of x is considered decreasing here. So that means for f double prime of x, this part right here, it's all considered negative. Okay? So for concave down, so that means it's from 0 to 4. And then, well, concave downwards, to put it right there. Okay, so concave downward for f of x is from 0 to 4. And then from the graph forward all the way to 8, almost 8, but things that's open circle, so 8's not included. So from 4 to 8, so that means f of x must be considered concave upward. Because this whole graph right here for f prime of x is positive. I mean, it's increasing. So if the function is increasing, so that means the next derivative will be considered positive. So the second derivative is positive right here. So that means it's considered concave upward. And state the x-coordinate of the point of inflection. So the point of inflections. So we do know that this one is concave down, concave up. So the point of inflection would be appearing at this position, which is 4. And then assume that f of 0 equals 0. Sketch the graph of f. Okay, so we do know that this part is positive, negative, positive. So it's increasing, decreasing. So it's increasing from 0 to 3. So here's what we got. Increasing from 0 to 3. And then from 3 to 4, it's decreasing. Well, from 3 to 5, it's decreasing. So that means at 3 right here. Okay, so there's a local max. So we just follow through what we found from the previous part right here, A, B, C, and D. And then down here at 5, we do have a local min. Okay, local min. Okay, it's all the way through. Okay, so now let's see what else that we have for the rest of this. So from 5, okay, let's see. So from 5 to 8. So the whole graph is also considered increasing. So from 5 to 8, so 5, 6, 7, 8. So that means the graph is also increasing. So here's what we got. And now, what about the rest of the part of the graph here? We don't know exactly what's happening afterward. So there's something wrong with this. So basically, just stop there. Oh, the reason why that I put in the like a sharp turn, because this point right here is discontinuous. So we can say that it's either like a vertical asymptote, or we can say that there's like a sharp turn here. So it's better for me to put in a vertical asymptote. Okay, so that means the graph is tended to going through this position. Getting close. Again, at this point, it's not differentiable because that is discontinuous. Okay, so let's see what else that we have for the rest of this. So this one, so we do have two problems. So two different functions. One is rational. It's a composition quadratic with rational. And the other one looks like it's exponential with a power that's irrational. so it's a little bit complicated. So find the vertical and the horizontal asymptote, if that's possible. Find the interval of increase or decrease. And then for C, find the local maximum and minimum values. And then for part D, find the interval of concavity and the point of inflection. And then part E, but that one is optional. So use the information from part A to D to sketch the graph. Okay, so what I would like to focus on is just from part A to part D. Okay, so now let's do the first one together. Okay, so let me just transfer this one to the next slide because we need more space. Okay, so all right, let's see. So what we got here for f of x, part A, it's a rational, but it's a composition of, well, the overall function is rational, but the inner function, it's quadratic. So we do have x squared over x plus 2 quantity squared. Okay, so once again, first thing that you want to find out, the first derivative. So f prime, well, you need to find the VA and HA. So the way to find VA, so you just want to set the denominator equal to 0. So set the denominator equals 0, and then solve for x. So that means x is -2. So that's your VA. And then for HA, so we do know that's a rational. It's the same power top and the bottom, so we basically take out the leading coefficient. So it's 1 over 1, or we can use the limit property. Limit x approaches infinity. The calculus technique, the way that we did it in chapter 2. So we take out the and behavior, so x squared, and try to expand this out, so it's x squared plus 4x plus 4. So that means the limit, x goes to infinity, so x squared over, again, the bottom part, I take out the and behavior, so x squared, so we got 1 plus 4 over x plus 4 over x squared. So if x is getting bigger and bigger, 4 over a very big number, so 0. 4 over an even bigger number, so it's going to be 0 again. X squared got canceled with x squared. So what's left is just 1 over 1. And then using the pre-calc technique, you can check that same degree top and bottom. So just check the leading coefficient. So it's 1. Okay, so now let's see the next part of the problem here. Back to what I have. Find the interval of increase or decrease. Okay, so that means we need to do the first derivative line test, because also it's going to help you to find out the local maximum and the minimum values. Okay, so let's see. Back to this slide here. So first derivative. So first derivative, we do have f prime of x. So it looks like we need to apply the quotient rule. Okay, so x squared, so then that'll be 2x derivative, times the denominator, x plus 2 quantity square, minus derivative of the denominator, so it's 2 times x plus 2, and then times the numerator, x squared. So again, this one is just the structure of the quotient rule. And then it's all over x plus 2 quantity to the power of 4. Okay? So now we need to find a critical number. So two ways that we can find a critical number. If you go back to the definition, we can either set the numerator equal to 0, or we can set the denominator equal to 0. But one thing that you need to know, so if the denominator equal to 0, so that's just the exact same value of the VA. So which means that it's impossible. So for -2, so basically this one you can just, cancel it out, because that's just the VA. Well, it's -2, not -4. Okay, let me just fix that one. So that one is -2, so that doesn't work because the VA. So the only thing we can set equal to 0 is just the top. So that we do have 2x, x plus 2 quantity square minus 2x squared times x plus 2 equals 0. And also from here we can take out the greatest common factor. If you see any greatest common factor here. Or another way you can do it, you can multiply everything out and then try to expand it. So it depends on which way that you prefer. So as a time consuming, I would like to take out the greatest common factor. So we do have 2x, x plus 2, things that they share in common. So what's left here? So that's just x plus 2. and then minus, well, 2x is gone, so we're left with just x right here. And also x plus 2 is gone. So x minus x, so that'll just give you 2. So we do have 2x times x plus 2. This one got cancel. Cancel. So that means 4x times x plus 2 equals 0. So for those two critical number, so which is what? X equals 0 and also x equals negative 2. But one thing is that x cannot be negative 2 because that's a VA. So at negative 2 there, it's a VA. So again, we don't put in that negative 2. Okay, so that one, negative 2 is a VA. We don't count it. So that means there's only one critical number. Okay, so we need to find out the increasing, decreasing interval. So I need to get to the next slide. So that means we want to do the line test. So 0. And this one, if you just do the AND behavior, the line test. So it's negative infinity to infinity. Again, negative 2, it's not included. So negative 2 right here. So just put in a little open circle. So you might be wondering, looks like we only got 2 interval here that we need to verify, but it's supposed to be 1, 2, and 3. Again, negative 2 there, that's the VA. So we're doing the first derivative line test. Again, the derivative that we have. So after we simplified it, let me just go back to that part right there. So try to simplify it all the way through. We do have 4x plus x over 2 over x plus 2 quantity to the power of 4. Okay, so let me just rewrite it. So it's 4x, x plus 2 over x plus 2 quantity to the power of 4. Again, this one cancels out, reduce, so it's 3. So for f prime of x, so we do have 4x over x plus 2 quantity to the power of 3. Okay, so now for the interval test, make sure that you need to put in 4x on top and then x plus 2 quantity to the power of 3 down the bottom because those are the factors. And then down the bottom here, it's all the result. So now let's find out the number we need to verify. Okay, let's use different color pen right here. So let's say negative 3. From negative 2 to 0, we can use negative 1. 0 to infinity, we can use 1. Okay, so negative 3 times 4, which is negative 12, so negative. Negative 3 plus 2, negative 1 to the power of 3, negative. So it's due negative, so negative times negative, which is positive. Again, this one is just the first derivative line test. So going back to part 1 of the lesson, so we do know that according to the first derivative line test, if first derivative is positive, that means f of x must be considered increasing. And now the next interval, we do have negative 1. So negative again, plugging that to 4x, so negative 4. So negative 1 plus 2, so 1 to the power of 3, positive. So negative times positive, which is negative. So that means for f of x is considered decreasing. And then 0 to infinity, so 0 to infinity, so we do have 1. So positive, positive, so that means positive. So it's increasing. Okay, so for that interval from negative infinity to negative 2, so the graph is increasing, same as from 0 to infinity. But anything that goes from negative 2 to 0, from the vertical asymptote to 0, it's considered decreasing. Okay, so later today I'm going to show you the graph for this instead of doing that manually. And now let's see the other part of the problem here. So we got A and B done. Find the local maximum and minimum value. Again, we find a critical number already. So all you need to do is just plug in a number back to the original equation. So we got the critical number, 0. Well, negative 2, again, that's a VA. That's not the max or min. Okay? So for 0, so let's plug in a number back to the original equation. So f of 0, so we do have 0 square plus 0 plus 2 quantity square. So it looks like it's 0 over a constant. Excuse me, let me just fix this. Undo. So 0 over constant, so that's just 0. So 0, 0. And guess what that is? Is that a max or a min? Again, this one it shows that negative to positive, so that means decreasing. And then increasing. So this one is actually the local minimum. Okay. And now let's see what else that we have for the rest of this. There's no local max because you had a point, it's just the VA. So find the interval of the concavity and the point of inflection. Okay, so that means, guess what? More work. Second derivative. So for first derivative, so that's what we got. So from here, use the quotient rule again. So we do have 4 times x plus 2, quantity to the power of 3, minus derivative of the bottom part. So we do have 3 times x plus 2 times 4x. And then this one, it's all over the denominator, quantity square. So you just square this whole thing here. So that would be power to power. So then that would be what? 6. And try to simplify that a little bit more. So the top part right here. So it looks like we can multiply this. And then we can take out the greatest common factor. Okay, so we try to take out the greatest common factor. We do have x plus 2. And then this one right here. So it can be written as bracket. So 4 times the quantity of x plus 2 square minus 12x all over x plus 2 quantity to the power of 6. Again, this one can be reduced to the power of 5. Okay, so let me just rewrite it. So the top part is just 4 times the quantity of x plus 2 square minus 12x, and it's all over x plus 2 to the power of 5. Okay, so now we need to find out the point of inflection. So again, the denominator cannot be 0 because that's a VA. So the only thing we can set equal to 0 is just the numerator, so which is 4 times x plus 2 quantity squared minus 12x. And then we try to expand it, so this one is just like 4 times the quantity of x squared plus 4x plus 4 minus 12x. So we got 4x squared, 16x minus 12x, then that'll be positive 4x. And then 4 times 4, 16 plus 16. So that equals 0. So we'll do this one on the next slide. So we do have 4x squared. So let me just write it down first. It is complicated and tedious, and it's time consuming as well. So guys, got to be patient with this. So this one's all positive. So for the next slide, so we're going to do that. Find the critical number. So again, second derivative. So we do have the top part. So we set that equal to 0. So we do have 4x squared plus 4x plus 16 over x plus 2 quantity square. I just want to check one thing. It's x plus 2 quantity to the power of 5. Okay, so set that equal to 0. So that means 4x squared plus 4x plus 16 equals 0. So take out 4. So we do have x squared plus x plus 4 equals 0. And it looks like this one is non-factorable. If this one is non-factorable, guess what you have to do? Either you want to complete the square or you want to use the quadratic formula. It is the quadratic formula. So negative b plus minus. It's very tedious. B squared minus 4ac all over 2a. So negative b, negative 1 plus minus square root of 1 square, 1 minus 4 times a. So 4 times 1 times 4. So 4 times 1 times 4, then that'll be minus 16. And you might be wondering, it's going to be imaginary number. So that, if it's imaginary number, so that means there's no real solution. So there's no real solution for the point of inflection. Okay, so no solution at all. Okay, so let me just go back and check that everything makes sense here. Okay, this one. So everything's positive. Yeah, looks like there's no solution for this. Okay, so now let's go to the graph. Okay, so the original function. So once you come up with the information, you can always sketch the graph manually. But instead of doing it manually, so here's what I would like to check on the calculator. So you can check all the work that you have done. So again, the original function is a quadratic, compositioning with rational and quadratic. So we put it into the graphing calculator. Okay, so let me just turn on the TI. Okay, so we'll see what that looks like. And then we'll do some graph analysis. Okay, you can just follow through what I'm showing here, the key history. So y equals, so let me just clear all this. So for y1, it's x squared divided by, well, the things that I need to bring down the power back. Okay, so I need to move the cursor. Divided by the quantity of x plus 2, quantity to the power of 2. Okay, so zoom 6. Again, at negative 2, you'll see that it's a vertical asymptote. That's why it's not showing here. Okay. So back to what we have done. Back to the first part, negative 2, that's the VA. HA, that's 1. So back to the graph that we have. See that 1 right here? That's a horizontal asymptote. And now increasing, so from negative infinity all the way to negative 2, so that's considered increasing. And then negative 2 to infinity, it's also considered, well, this one is considered decreasing. So check that, what we have done. Okay, back to this part right here. Wait a minute. Let's see. So that's part A, part B. We find a critical number. Okay. So negative infinity to negative 2. So that's increasing. So that's what we got. And then everything else from negative 2 to 0, 0 to infinity. Well, negative 2 to 0 is actually decreasing. So let's see. Yeah, negative 2 to 0, that's decreasing. And then 0 to infinity, this part is actually considered increasing. And that's what we have done. And then 0, 0, that's a local min. There's no local max here because this one goes all the way up to infinity. Okay? So another thing that you might be considered doing is about the concavity. We didn't do the concavity test yet. So one thing we do notice that there's no point of inflection, but we can still do the concavity line test by using the second derivative. So let's see, let's go back to this part right here. So what you need to finish for part D, so you want to do the line test for the second derivative. We do know that there's no point of inflection, but one thing we do know is that x cannot be negative 2. So we're at negative 2, so open circle. Again, negative infinity to infinity. So let's just plug in a number. So let's say negative 1, no, negative 3. And then over here on the right hand side, you want to put in 0. So back to the second derivative. So you plug in negative 3. So this one will give you positive on top. And then down the bottom, that will give you negative. Okay, well, let's see. So negative 3. So negative 3 quantity squared, that's positive. 9 times 4, 36. So 4 times negative 3, negative 12, plus 16. So the whole thing here on top is positive. But down the bottom here, So that one is going to be negative, because negative to the power of 5 is still considered negative. So positive over negative, then that's going to be negative. So that means from negative infinity to negative 2, then that'll be considered concave down. And then from negative 2 to infinity, so let's plug in 0, so positive, positive, so it's all positive. So this one's concave down, this one is concave up. And then back to the graph that we have done. Well, actually, they're both considered concave up. So there's something wrong with the second derivative. Well, this part right here, that's concave up. That's right. But this part of the graph here, it's also considered concave up. Okay, let me check this one real quick. Okay, so what I did, I reduced it already. It's 5. Okay, 4 right here in the front. We take out the... Okay, let me go back to the previous slide. Yeah, that might be something wrong with the error, the sign change that we found. Okay, so they're both considered positive. We try to do the second derivative line test. Okay, so I would like to recheck the problem and see what happened. Okay, so now let's try the last one. So the last one is quite similar to the setup that we have. So first thing that you want to do, find VA, HA. So this one is written as e to the power of negative 1 over x plus 1. So obviously the VA would be considered negative 1. Okay? And then for HA, okay, so this one it's a little bit weird. It's not just rational, but it's exponential. So it looks like there's no... Well, if you just look at this part right here for HA, then that'll be considered 0. So e to the power of 0, then that'll be 1. Okay? So for the horizontal asymptote, if you take that to the infinity, so this power here, so eventually it's approaching to 0. So e to the power of 0, then that'll be considered 1. Okay? And then for the rest of that, you want to take the first derivative, second derivative, find the local max, local min, do the concavity line test. So now, instead of doing like this way, so we just want to do some kind of graph analysis for this. So let's put it into the calculator and see what happened. So the function we have, so e to the power of negative 1 over x plus 1. Okay, so let's see for the graph. Okay, so let me just clear all this. So for that one, we do have power e. Okay, so second, natural log, so that's e to the power of quantity. So negative 1 over the sum of x and 1. Okay, parentheses, and then parentheses one more time. Okay, so and now let's see. Go to zoom and then hit 6. Now for one of the section, we're going to be doing more this precisely. Okay, so we're going to have more practice problem like this. Okay, so as you can see that here, the VA that we found, which is considered negative 1. Okay, so negative 1. So it looks like this one, there's no max, there's no min, and also there's no any point of inflection. So that means we're using the point on the VA as the position for the line test, for the first derivative and the second derivative line test. So as you can see that this part from negative infinity to negative 1, so it's all increasing, so that means the first derivative is always positive. And it's concave upward, so that means the second derivative line test. So from negative infinity to negative 1 is also being positive. And then over here it's also positive for the first derivative line test, because it's all increasing. But for the second derivative, the line test would be considered negative, because that shows concave downward. So there's so many things that you have to go through for this problem, because this one is considered rational and exponential for the compositioning. Okay, So for the homework of this part 2 of the sections, I would like you to do the best you can. Again, just find VA, HA, and then do the line test. There's no need to worry about sketching the graph yet. So one of the sections in the future will be doing that. Okay? So thank you for watching the video today, and I'll see you guys next time.